Success was born from failure in the medieval world. We are exploring the machine that only works when it's broken, a true paradox from the age of castles and cathedrals. You will discover how ancient engineers designed systems that achieved their peak performance only after they were cracked, bent, or deliberately damaged. How could a shattered siege engine throw stones farther than a perfect one? Why would a farmer intentionally break his plow before using it? By the end, you will possess a forgotten framework for innovation, one that sees weakness not as a flaw, but as a hidden source of strength. What does our own pursuit of perfection prevent us from building today? To grasp the existence of a machine that thrives on its own flaws, we must first step into the mental workshop of the medieval world. This was not a dark age of simple thinking, but a period illuminated by the brilliant, flickering light of paradox. Scholars and monks spent centuries wrestling with concepts that defied straightforward logic, questions of faith and philosophy where two contradictory truths could coexist. They pondered how a divine being could be both one and three, or how free will could operate under a predetermined plan. This constant engagement with intellectual contradiction trained the medieval mind to see brokenness not as an end, but as a potential beginning. Theologian Thomas Aquinas, for instance, meticulously explored the nature of God through a lens of logical impossibilities, framing debates that resonated from the university to the artisans' guild. When a craftsman encountered a fractured gear or a cracked support beam, this cultural backdrop offered a different perspective. A failure in the physical world could be a mirror of a greater spiritual paradox, a puzzle to be decoded rather than a mistake to be discarded. This unique intellectual environment gave artisans the freedom to experiment, to deliberately introduce a flaw into a design and observe the unexpected outcome. Their records, carefully kept in monasteries and guild halls, reveal a startling willingness to work with rather than against imperfection. This foundational philosophy of embracing contradiction is the very key that unlocks the first remarkable story of a machine that only worked because it was broken. The chronicles of a 12th century siege outside the walls of Carcassonne tell of a weapon that defied all reason. While other trebuchets were built for flawless symmetry and strength, the master engineer in charge of this particular machine ordered his crew to strike its main timber beam with heavy mallets. They did not repair the resulting splintering wood, they celebrated it. This was the birth of the so-called cracked catapult of Carcassonne, a machine that only achieved its legendary accuracy after its arm was deliberately fractured in a very specific pattern. Rival armies watching from the castle walls must have laughed, confident they were facing a crew on the verge of catastrophic failure. Their laughter turned to dread when the first stone was launched. It flew farther and struck with more force than any projectile from a perfect machine. Its arc through the air an unpredictable, wobbling path that made it impossible for defenders to intercept. The broken trebuchet did not just work, it performed better than any of its intact counterparts. How could this be possible? The answer lies in the nature of stress and release. A perfectly sound timber arm is rigid, transferring the energy of the falling counterweight in a single, violent jolt. This efficiency comes at a cost. The immense strain can shake the entire frame apart, and the trajectory is as predictable as the sunrise. The cracked arm of the Carcassonne machine, however, behaved differently. Its network of fractures acted like a set of microscopic hinges, absorbing and redistributing that explosive energy along its entire length. Instead of one brutal shock, the arm unfurled, whipping forward in a complex wave motion that imparted more force to the projectile and sent it flying on a novel, erratic course. The operators were not just breaking their machine, they were tuning it. They learned through painstaking trial and error which fracture patterns yielded the most power, using controlled impacts to calibrate the breakage like a musician tuning a string. This was not an act of desperation, it was a sophisticated engineering protocol. It forces us to confront a radical idea that structural integrity might not always mean perfection. Sometimes true strength is found in a calculated weakness, a deliberate flaw that allows a system to move and breathe in ways a perfect one never could. This paradox of the broken beam leads us directly to the humble farm, where another seemingly broken tool revealed a similar secret. The secret of the broken trebuchet arm lies in the physics of stress itself. A flawless wooden beam is strong, yes, but it is also rigid and unforgiving. When the immense force of a falling counterweight strikes, that energy has nowhere to go. It travels through the beam in a single, violent shockwave, a jolt that threatens to shatter the entire machine and sends the projectile on a predictable, easily intercepted arc. But introduce a carefully placed crack and everything changes. That fracture acts not as a failure but as a release valve. It forces the stress to redistribute, to find new, more complex pathways through the material. Instead of one brutal shock, the energy ripples through the beam in a controlled wave, a phenomenon medieval engineers witnessed but could not name. This redistribution of force allows the arm to unfurl like a whip, imparting far more energy to the projectile and sending it flying on an unpredictable, devastating path. This same principle applied to the humblest tools. A farmer might find that a cart with a slightly warped axle actually rolled more smoothly over deeply rutted roads. The bend allowed the wheel to absorb the bumps and shocks that would otherwise jolt the entire cart, a primitive but effective form of suspension born from a flaw. The second hidden force is resonance. Every object has a natural frequency at which it vibrates. A perfect water wheel, for instance, might fight against the river's current, its rigid structure creating jarring vibrations that waste energy and strain its axles. But a wheel with a minor fracture or a deliberate imperfection could have its resonant frequency altered. It might then fall into sync with the rhythm of the flowing water, turning with a new, fluid efficiency that reduced wear and tear. Medieval clockmakers saw this too. A perfectly machined gear train could be thrown off by the slightest tremor, but a mechanism with a tiny, almost imperceptible flaw might actually dampen those vibrations, allowing the clock to keep more accurate time. These builders were masters of observation, not theory. They did not have equations for stress redistribution or resonant frequency. Instead, they kept meticulous records, noting how a chipped gear tooth sometimes reduced friction, or how a splintered mill shaft lasted longer than a pristine one. They learned to listen to their machines, to hear the difference between a destructive break and a functional one. Broken in their hands was not a state of ruin. It was a different kind of order, a functional optimization achieved not by fighting nature's imperfections, but by working in concert with them. This profound understanding was entirely dependent on the very substances they shaped with their hands. That deep, intuitive understanding of material science was the craftsman's daily reality. A master carpenter walking through a forest was not just looking for straight, strong trees. He was reading a story written in wood, searching for a specific character flaw. He might bypass a perfectly straight oak in favor of one with a pronounced spiral grain, knowing that when carved into a ship's mast, that twisted internal structure would make it uniquely resilient to the ocean's powerful, twisting forces. For a cathedral's roof, he would not see a knot as a simple defect to be cut out. He would identify it as a natural stress point and place the beam so that the knot absorbed and dissipated the immense weight pressing down from above, turning a potential weak spot into a built-in relief valve. This philosophy extended to the forge. A blacksmith quenching a newly forged sword blade would watch the play of colors on the metal, a visual map of its internal crystalline structure. He knew that a blade that cooled with absolute perfect uniformity could be dangerously brittle. Sometimes a slight variation in the carbon content, what we would call an impurity, was a secret weapon. It could create a subtle gradient of hardness, giving the sword a razor-sharp edge that seamlessly transitioned into a flexible, shock-absorbing spine, a blade that would bend in a deadly clash rather than snap. These artisans were not just building things, they were collaborating with the inherent nature of their materials, guiding their unique personalities into a final, functional form. This acceptance of heterogeneity stands in stark contrast to our modern quest for flawless, identical copies. We see a knot in the wood and discard it, seeking perfection. They saw the same knot and asked a different question: what can this specific imperfection do for me? This foundational principle, that a material's flaws are integral to its function, set the stage for the most widespread application of this paradoxical engineering, found not on the battlefield but in the farmer's field. That same philosophy of the deliberate flaw was dragged across the fields of medieval Europe, not by engineers but by farmers and their oxen. The heavy iron-tipped plow was a vital tool, yet its very strength was its greatest weakness in rocky, uneven soil. A perfectly rigid plowshare would fight the land, hitting every hidden stone with a jarring impact that strained the oxen and often snapped the wooden frame. But farmers discovered a secret: a new plow, deliberately forged with a thin, brittle section in its moldboard, performed poorly at first. It needed to be broken in. After a few passes through the field, a crack would form, a controlled fracture that village blacksmiths knew how to induce with a precise strike from a wooden mallet. This was not a sign of a faulty tool, it was the moment the plow awakened. The initiation fracture transformed the rigid iron into a semi-flexible system. Now, when the plowshare hit an obstacle, it could flex and shudder, absorbing the shock instead of transmitting it back through the entire frame. This slight give allowed the blade to follow the natural contours of the earth, creating a straighter, deeper furrow with significantly less effort from the draft animals. The broken plow did not fight the land, it danced with it. Manuscripts from the 14th century illustrate these plows with their engineered weak points, and agricultural texts carefully detail the ritual of breaking in a new tool. The best village smiths were not famed for making the strongest plows, but for crafting those that would develop the perfect fracture pattern, a secret so valuable it was guarded within certain craft families for generations. Here, failure was not an accident, it was the final, crucial step in the manufacturing process. The paradoxical plow demonstrates that controlled breakage could lead to superior performance in the most mundane of tasks, a principle that then reached for the heavens, etched into the stone of the great cathedrals themselves. High above the fields and forges, the ultimate expression of paradoxical engineering reached for the heavens in stone and glass. The master masons who built the great Gothic cathedrals were the supreme alchemists of imperfection. A visitor gazing up at the intricate vaulting of a nave would see a vision of divine harmony, but hidden within that sacred geometry was a crucial, deliberate mistake. In one famous cathedral, the great rose window is not perfectly centered on its axis. It is offset by a distance you could barely measure with your hand, a purposeful error in a structure demanding absolute precision. This was not a sign of poor workmanship, it was a calculated act of genius. The perfectly symmetrical design, for all its beauty, creates predictable stress points, rigid lines of force that could amplify the slightest shift in the foundation or the relentless push of the wind. But introduce a single, subtle asymmetry and everything changes. That off-center window or a keystone cut with one unusual facet forces the immense weight of the stone to redistribute itself. The loads travel along new, more complex pathways, creating a web of tension and counter-tension that makes the entire structure more resilient, more able to settle and breathe with the changing seasons and the slow movement of the earth below. Modern engineers using computer modeling have confirmed what the masons knew through intuition and experience. These flaws create a beneficial tension distribution that a perfect design simply cannot achieve. The theological justification was equally profound. The builders believed that only God could create perfection. For a human to attempt it in a house of worship was the height of arrogance. By intentionally including a single flaw, they acknowledged their own fallibility, creating a space that was both awe-inspiring and humbly relatable. The cathedral, therefore, does not triumph over its imperfections. It stands majestic because of them. Its enduring strength is a monument to the power of acknowledged weakness. This same sophisticated understanding of rhythm and counter-rhythm, of finding stability through controlled imbalance, was quietly at work in the era's most advanced machines, the great cathedral clocks that measured the hours of prayer. Inside the towering cathedral clocks of Prague and Strasbourg, time itself was governed by a paradox. The most vital component, the escapement, was a delicate piece of brass and iron that controlled the release of the clock's power, the steady tick-tock that measured the hours for prayer and commerce. Yet horologists discovered that a brand-new, perfectly machined escapement was often a liability. Its flawless teeth would engage with the crown wheel in a series of tiny, jarring impacts, creating a phenomenon called backlash, an inconsistent stutter that robbed the clock of its rhythm and introduced frustrating inaccuracies. The solution, documented in secretive guild manuscripts, was not to build a better part but to break a good one. A master clockmaker would take a new verge escapement and with a small file, deliberately chip or wear down one of its pallets. This was not an act of vandalism but one of the highest precision. The introduced flaw changed the entire dynamic of the mechanism. Instead of a sharp, percussive engagement, the worn pallet created a softer, more rounded interaction with the crown wheel. This subtle modification dampened the destructive vibrations and minimized that erratic backlash, allowing the pendulum to swing with a newfound metronomic consistency. The clock did not simply tolerate this damage, it required it to function at its best. This was the secret of the fractured escapement, a machine that told true time only when one of its hearts was slightly broken. The most revered clockmasters guarded this knowledge closely, often filing new parts in private to mimic the perfectly broken-in state of an older, reliable mechanism. They understood that wear and tear was not just an inevitable enemy to be fought. It was a force that could be anticipated and even harnessed as a fundamental design parameter. This principle of calibrated degradation echoed beyond the clock tower, finding a powerful expression in the relentless motion of the watermill. The steady rhythm of a perfect waterwheel could be its own undoing. Along the rushing streams of medieval Europe, where these mills were the engines of industry, observant millers witnessed a baffling truth. A wheel with one or two broken or missing buckets often ground grain more consistently and efficiently than a flawless, fully intact one. This was not a symptom of damage but a sign of optimization. The secret lay in the disruption of a destructive rhythm. A perfect wheel, with its identical buckets striking the water in a steady, metronomic beat, transferred that regular pulse all the way up through the gears to the millstones themselves. This created a persistent, low-frequency vibration, a kind of mechanical hammering that could slowly shake the heavy stones out of their precise alignment. When the stones shifted even slightly, the gap between them would change, leading to poorly ground flour or catastrophic friction. But a single missing bucket shattered that monotonous rhythm. It introduced an irregular cadence, a hiccup in the wheel's rotation that broke up the resonant vibration. The entire system, from the axle to the grinding stones, was jolted out of its destructive pattern, settling into a more stable and productive operation. This irregular pulse delivered a second crucial benefit. It kept the wheel clean. The smooth, predictable flow of water around a perfect wheel allowed leaves, silt, and other debris to cling to the buckets, slowly building up a heavy, inefficient coating. The gap created by a missing bucket, however, churned the water into a localized turbulence. This miniature whirlpool acted as a natural scouring agent, constantly washing away accumulating debris before it could impair the wheel's balance and performance. This meant fewer work stoppages for manual cleaning and more hours spent productively grinding grain. Millwrights, seeing this principle in action, stopped waiting for accidents to happen. They began constructing wheels with intentionally omitted buckets. OR Chinese letter deliberately weakened the joints on specific ones using precisely placed grooves. These designated buckets were designed to break away cleanly during a sudden surge of high water, a self-sacrificing act that instantly optimized the wheel for the new, faster flow rate. They had engineered a system that was not merely robust but adaptive, one that used a deliberate loss of components to trigger a gain in total system efficiency. This acceptance of a beneficial flaw extended even to the most delicate of technologies, the fragile lamps that pushed back the medieval night. The heat inside a master smith's forge was not born from a perfect vessel, but from a fractured one. A newly built furnace, with its clay and stone lining smooth and unblemished, was a frustratingly inefficient tool. It would burn unevenly, creating cold spots that left ore only partially smelted and producing a brittle, unreliable metal. The true magic began only after the furnace was seasoned, a weeks-long ritual of running it at its absolute limits until a specific web of hairline cracks spread across its inner walls. Guild records describe this process not as a repair but as an awakening. The master smith would watch the emerging fracture pattern with the careful eye of a gardener, for these cracks were not failures. They were a meticulously engineered ventilation system, etched into the very fabric of the furnace by heat and stress. Each tiny fissure acted as a miniature flue, drawing in precise amounts of air to create micro-drafts across the burning charcoal. This network of flaws introduced just the right amount of oxygen to achieve a cleaner, hotter burn, eliminating cold spots and raising the temperature to a point where steel could be worked with a consistency that was the envy of rival towns. The smith did not fight these cracks, he cultivated them. He knew that a perfectly sealed furnace would choke on its own exhaust, while a completely broken one would lose all its heat. The ideal state was a controlled, fractured one, a delicate equilibrium where the flaws managed the fire. This mastery over imperfection allowed medieval metallurgists to achieve metallurgical feats that are difficult to replicate even with modern refractory materials, all because they understood that the path to a perfect blade began with a broken furnace. This sophisticated use of calculated weakness for superior function was a principle that extended from the heart of the workshop to the very walls built to defend a town. That same principle of strategic weakness found its ultimate expression in the town's main gate, a massive barrier of banded oak and iron. Its true strength was not revealed in its pristine state, but after its first brutal test. Defenders noticed a strange phenomenon, a gate that had been battered by a ram. Its heavy iron hinges now visibly bent and warped, would often hold stronger against the next assault than a brand new, perfectly hung one had. The secret lay in the geometry of failure. A flawless gate pivoted smoothly on its hinges, focusing the full, concussive energy of a ram's blow directly onto its central lock and bolt. This single point would bear the entire strain, a design flaw that often led to a catastrophic, splintering failure. But a gate with bent hinges was a different beast entirely. The deformation shifted the pivot point, causing the entire structure to twist and bind against the stone archway of the gatehouse the moment it was struck. This friction was its salvation. Instead of a concentrated shock to the lock, the force of the impact was now smeared out, distributed across a much wider area of the stonework and the gate itself. The ram was no longer striking a door, it was trying to push over a section of the wall. Town carpenters and blacksmiths, observing this natural reinforcement, stopped waiting for an enemy to do the work. They began installing new gates with hinges that were deliberately pre-stressed, hammered or forged with a slight, calculated bend. In some towns, the final step in a gate's construction was a ritualized beating, where guards would use a heavy log to strike the closed gate repeatedly, not to test its strength, but to induce the exact type of beneficial deformation that would grant it true resilience. Municipal fortification manuals from the period explicitly advised this practice, instructing builders to test a gate to failure during construction, to identify and then meticulously replicate the precise breakage that made it stronger. The gate that held stronger once its hinge was bent is a perfect metaphor for the medieval engineering mindset. The first line of defense was not designed to be impervious, but to be intelligent. It was meant to fail, but only in a specific, controlled, and ultimately reinforcing way. This acceptance of a beneficial first strike was a philosophy that armored men, not just walls, and it would change the nature of personal combat forever. A knight's polished breastplate was a canvas for a brutal kind of artistry. That mirror-smooth surface, for all its intimidating shine, presented a predictable geometry to an opponent's sword or lance. A skilled fighter could anticipate exactly how his blade would skid across that flawless curve, but a breastplate marked by a deep gouge from a past battle, or a cluster of smaller dents near the shoulder, changed the entire equation. These were not mere scars, they were functional topographies. Each imperfection acted like a miniature baffle, catching the tip of a weapon and redirecting its force in an erratic, unpredictable manner. A strike that should have glanced away cleanly might instead be twisted violently to the side, wrenching the attacker's arm and leaving him exposed. This was not random damage, it was a layer of defensive chaos engineered directly into the metal. The most sought-after armorers in Milan understood this principle intimately. For their most discerning and wealthy clients, they performed a service known as proofing beyond the standard test. Before delivery, a new suit of armor would be methodically struck with blunted hammers and practice swords, not to test its strength, but to improve its function. The craftsman would create a specific pattern of controlled dents and shallow gouges across the breastplate, pauldrons, and gauntlets. This preconditioning was a mark of the highest expertise, a service that commanded a premium price because it acknowledged a profound truth about combat. Perfection was a liability. A suit of armor was not a static shield. It was an active component of a warrior's defense, and its performance could be enhanced by introducing the right kind of weakness from the very beginning. The warrior wearing this pre-broken armor carried a subtle, invisible advantage. Every deflected blow was now a product of chaotic physics his opponent could not calculate, turning the inevitable reality of damage into a preemptive tactical victory. This same logic of turning expected failure into a functional feature was applied to objects far removed from the battlefield, even to the simple clay jugs used to carry water from the well. A household pot gleaming with a perfect, unbroken glaze was a disaster waiting to happen. In the kitchens and storerooms of the medieval world, the most reliable ceramic jars were not the flawless ones, but those covered in a fine, web-like pattern of surface cracks. Potters called this crazing, and it was the sign of a superior vessel. A pot sealed with an impermeable glaze might look ideal for storing water, oil, or fermenting ale, but it was dangerously fragile. As temperatures changed or fermentation gases built up inside, the trapped pressure had nowhere to go. The result could be a catastrophic failure, a sudden crack that split the pot in two, or even a violent explosion of ceramic shards and contents. The crazed glaze offered a brilliant solution. This network of microscopic fractures did not mean the pot was leaking, far from it. Instead, it acted as a sophisticated pressure management system. The cracks were so fine that surface tension would still hold liquids securely inside, but they allowed minute amounts of air and vapor to pass through the clay body. The pot could now breathe, equalizing the internal and external pressures with every shift in the weather or every bubble from active yeast. This prevented the destructive stresses that would shatter a perfectly sealed container. Achieving this beneficial brokenness was an art in itself. A master potter did not leave it to chance. He would carefully control the cooling of his kiln, shocking the hot pots with drafts of cooler air to induce a specific pattern of thermal stress. Alternatively, he would apply a special mineral wash to the glaze before firing. This wash was formulated to contract at a slightly different rate than the underlying clay as the pot cooled, guaranteeing the formation of the desired microscopic flaw pattern. This was not a manufacturing defect. It was the final, crucial step in the creation of a truly durable pot. Merchant ledgers from port cities often listed these items at a premium, specifically noting jars with good cracking as being more valuable for long sea voyages where changes in humidity and temperature were extreme. Here, in the most humble of objects, we see the entire philosophy of paradoxical engineering crystallized. The path to being truly leak-proof was to first become, in a controlled and microscopic way, broken. This acceptance of a necessary flaw for greater systemic resilience would soon guide explorers far beyond the sight of land, relying on instruments that were only accurate once they had been bent by the ocean itself. A navigator on a swaying ship deck trusted an instrument he knew was not perfect. The most prized astrolabes, intricate maps of the heavens etched in brass, often contained a secret flaw. Their latitude limb, the ring used to set the instrument for a specific location, was sometimes deliberately bent by the craftsman, creating a slight but crucial misalignment. To the untrained eye, this warping was a sign of a ruined device, but for the experienced sailor or astronomer, it was the source of its unparalleled accuracy. This was not a manufacturing error, it was the final, masterful step in calibration. The atmosphere itself bends starlight, a phenomenon called refraction, which makes celestial bodies appear slightly higher in the sky than they truly are. A perfectly straight astrolabe would measure this illusion, leading to dangerously incorrect calculations of latitude. The bent limb, however, acted as a built-in correction. By offsetting the scale just enough to counter the average refraction at a particular latitude, it cancelled out the sky's deception, yielding a truer position from a false reading. Geoffrey Chaucer, in his own treatise on the astrolabe, alluded to this practice, advising that a new instrument must be compared against known stars and then adjusted for its persistent error. This did not mean the device was faulty. It meant the universe was complex, and the tool needed a compensating flaw to speak its truth. The paradoxical astrolabe teaches us that absolute precision in every part can lead to a greater systemic error. True accuracy was a holistic achievement, a dance between the ideal geometry of the instrument and the messy, refractive reality of the world it was designed to measure. This sophisticated embrace of a compensating flaw, where a deliberate error in the part creates a more profound truth in the whole, resonates far beyond navigation. It finds a stunning parallel in the sacred spaces of the time, where architects designed not for visual perfection, but for an acoustic truth that could only be unlocked by irregularity. The most beautiful music sometimes emerged from a broken instrument. In the candlelit courts of medieval Europe, where the lute reigned as the instrument of poets and nobles, master luthiers held a quiet secret. A lute that had never known a crack often sounded thin and sharp to their discerning ears, while an instrument whose soundboard had fractured and been expertly repaired could possess a voice of unparalleled richness and soul. This was not a superstition, it was a physical reality. When a crack appeared in the delicate spruce wood of the soundboard, the repair process was a form of acoustic surgery. The luthier would not simply glue the seam shut. He would painstakingly fit tiny, tapered inserts of wood into the fracture, creating a complex network of new grain patterns and glue lines across the vibrating surface. This repaired web acted as a sophisticated filter. It dampened certain brittle, high-frequency overtones that could give the music a harsh, metallic edge, while simultaneously allowing the warmer, more resonant midtones to bloom and sustain. The result was a tonal character that musicians described as having more depth and complexity, a voice that felt both ancient and immediate. This understanding was so profound that luthiers began to replicate the effect on brand new instruments. They would use delicate scrapers to thin specific areas inside the soundboard, creating zones of controlled flexibility that mimicked the vibrational damping of a healed crack. Others added asymmetrical internal bracing, patterns that would have been considered flaws in a less enlightened workshop, all to grant a new lute the instant character of a venerable, well-traveled instrument. Guild records from cities like Nuremberg detail these techniques not as tricks, but as the highest level of the craft, a way to build the memory of past stress directly into the wood. The lute, therefore, becomes a powerful metaphor for this entire engineering philosophy. Its sweetest song was not born from a state of pristine, untouched perfection, but from a history of damage that had been acknowledged, integrated, and mastered. This principle of building upon past stress was not confined to silent, solid objects. It flowed just as powerfully through the engineered waterways and liquid systems that drove the era's growing industries. Even the grandest aqueducts sometimes needed a little help from a well-placed clog. In the water systems of medieval cities like Siena and Bruges, engineers observed a phenomenon that defied simple logic. A channel flowing perfectly clear and unobstructed was not the ideal state. Over time, such a channel would allow silt and debris to settle gently across its bottom, slowly choking its own capacity. The true engineering marvel occurred after a partial blockage formed, perhaps from a fallen branch or a pile of accumulated leaves at a narrow point. This obstruction was not a crisis, it was the start of a purification cycle. The blockage caused the water to pool and pressurize immediately upstream, building a temporary reservoir of potential energy. This pressurized water then accelerated through the narrowest point of the obstruction with enough force to scour the channel bed clean, picking up the settled silt. Finally, the released surge would carry that suspended sediment far down the system, often past multiple settling basins in a powerful, self-cleaning pulse. Maintenance logs reveal that the engineers did not wait for nature to provide this service. They would deliberately insert temporary wooden dams or leave certain intake grates partially closed, orchestrating these beneficial blockages to occur at regular intervals. They were, in effect, programming a controlled failure into the system to prevent a much larger, uncontrolled one. A perfectly clear channel led to stagnation and decay, while a channel with a calculated flaw maintained its own vitality. This represents a profound leap in thinking, from focusing on the performance of individual components to optimizing the behavior of the entire network. The system's greatest efficiency was achieved not when every part worked perfectly in isolation, but when a single, strategic imperfection introduced a dynamic, self-regulating rhythm to the whole. This sophisticated understanding of systems, where a local problem creates a global solution, mirrored the very structure of the guilds and communities that built these marvels. A master glassblower's most treasured formula was sometimes his most generous gift to a rival. The craft guilds of medieval Europe built their power on a foundation of impenetrable secrecy, guarding their technical knowledge behind sworn oaths and locked chests. Yet the records of the Venetian glassmakers, for instance, reveal a startling paradox. Their council would occasionally permit a specific, advanced technique for creating crimson glass to be leaked to a competing guild in a distant city. This was not an act of carelessness, but one of deep strategic calculation. The leaked knowledge was a carefully crafted lore, a partial truth. It might detail the ingredients but omit the precise temperature curve of the annealing oven, or it would specify the type of sand but leave out the crucial stirring rhythm that introduced tiny, light-scattering bubbles essential for the color's depth. When the rival guild triumphantly produced their own version, it would be inferior, a dull imitation that only served to enhance the prestige and mystery of the original Venetian product. More importantly, the act of leaking forced the home guild into a state of heightened innovation. Knowing that competitors were now working with a fragment of their knowledge, the master craftsmen had to push their own art forward, developing new colors and techniques to stay ahead. Their ledgers show deliberate entries for the cost of sending a journeyman to a rival city with instructions to be overheard in a tavern, a calculated investment in their own obsolescence. Why would any organization willingly give away its crown jewels? Because they understood that absolute, static secrecy led to stagnation. A guild that never shared anything risked becoming an isolated, inbred institution, its techniques growing rigid and outdated. By allowing a controlled fracture in their wall of secrecy, they created a dynamic pressure, a creative tension that fueled a cycle of perpetual advancement. The guild itself became a kind of living machine, one that achieved its greatest vitality not when its knowledge was perfectly contained, but when it was allowed to breathe and interact with the world in a managed way. This social engineering mirrored the physical principles of the cracked catapult and the bent gate, proving that the paradox of strength through weakness was not just a property of wood and iron, but of information and community. And just as a guild could weaponize a leaked secret, so too could a general on the battlefield turn a planned retreat into his greatest victory. A broken arrow shaft raised high above the chaos of the fray could be the most powerful weapon on the field. While the enemy saw a standard of distress, a sign that the opposing line was cracking, your own soldiers saw a pre-arranged command to begin a carefully choreographed collapse. This was the heart of the broken arrow signal, a tactical deception that weaponized misinterpretation. At battles like Agincourt, chroniclers noted how English commanders used seemingly damaged or captured standards to lure the proud French cavalry into a fatal trap. The French, believing the broken signal indicated a routed enemy, would charge headlong into a killing zone of hidden archers and prepared stakes, their own momentum becoming their executioner. For this ruse to work, it demanded an almost unthinkable level of discipline from the common soldier. You are a man-at-arms watching your commander's banner fall or seeing a signal of apparent retreat. Every instinct screams to stand your ground or to flee in genuine panic. Yet you have been drilled to understand that this very symbol of chaos is the key to victory. You break ranks not in fear but in faith, trusting that your controlled disorder is drawing the enemy into a snare. The system's success relied entirely on its dual nature, a message that was perfectly clear to your own side and perfectly misleading to the foe. This was communication engineered to fail in the open, yet succeed in secret. The broken arrow was not a flawed command, it was a flawless trap disguised as a flaw. This high-stakes principle of profiting from apparent loss did not remain on the battlefield. It marched directly into the counting houses and market squares of the growing medieval towns. Even a clipped coin could buy a loaf of bread when a perfect one was nowhere to be found. In the bustling market of a 14th-century town, the reality of daily commerce was not a purse full of pristine silver pennies fresh from the royal mint. It was a jangling collection of worn and irregular discs, many with their edges shaved away, their official stamps blurred by time and countless hands. This practice of clipping was a crime, to be sure, punishable by the loss of a hand or worse. Yet, in a profound paradox, this systematic breaking of the currency was often the very thing that kept trade from grinding to a complete halt. The official money supply, controlled by a distant king, was rigid and often scarce, especially in regions far from the sources of silver and gold. A perfect, unclipped coin was hoarded, taken out of circulation by wealthy merchants or nobles, creating a desperate shortage of small change for everyday people to buy food, pay rent, or purchase a few nails from the blacksmith. When a merchant clipped a tiny sliver of silver from the edge of 100 coins, he was not just stealing, he was performing an act of unsanctioned monetary policy. That accumulated silver could be melted down and pressed into new, if unofficial, coins, while the original, now lighter coins continued to circulate. The total number of physical coins in the marketplace increased, providing the essential liquidity for the economy to breathe and function. Town records show that local authorities, faced with the stark choice between empty markets and a degraded currency, often chose to look the other way. They understood that a broken system that worked was infinitely better than a perfect system that had seized up entirely. The true sophistication, however, lay in the marketplace itself. Merchants and stallholders were not fools. They did not accept every coin at its face value. They became expert assessors, weighing coins on small, portable scales and judging their worth based on visible wear and the severity of their clipping. A penny might be valued at 3/4 of a penny, or half, creating a de facto system of variable pricing that adapted fluidly to the actual metal content available. This was a grassroots, flexible monetary policy long before the concept had a name. The economy of clipped coins teaches us that resilience can emerge from corruption, and that a system's overall health sometimes depends on tolerating, or even relying upon, its localized failures. This acceptance of a beneficial impurity was a principle that medieval healers applied not to metal, but to the human body itself. A physician's most effective treatment sometimes began only after the tool had fallen away. The medieval barber surgeon, applying his wriggling leeches to a feverish patient, was not aiming for a single, dramatic loss of blood. His true objective was more subtle. He watched carefully for the moment the engorged leech would naturally detach and drop off. This was not the end of the procedure, but the start of its most crucial phase. The small wound left behind would often continue to ooze for hours, a slow, persistent seepage that some practitioners came to believe was far more beneficial than the initial, vigorous flow. This secondary bleeding represented a broken state for the body, a failure of the wound to close and heal with proper speed. Yet within this failure they saw a therapeutic process. The rapid blood loss of the primary phase could induce weakness and shock, violently upsetting the patient's delicate balance of humors. The slow seepage that followed, however, was a gentle, sustained purge. It was thought to patiently draw out the corrupt, excess humors causing the illness without depleting the patient's vital strength. Medical texts, heavily influenced by the ancient teachings of Galen, even advised methods to prolong this state. A surgeon might apply a poultice of certain herbs like marshmallow root to the wound, not to staunch the flow, but to gently irritate the tissues and prevent clotting, engineering a controlled, ongoing failure of the body's natural healing response. While we now know the humoral theory itself was flawed, the underlying logic of the treatment is strikingly familiar. These medieval practitioners were not trying to fix a broken system with a perfect, immediate solution. Instead, they guided the body into a state of managed dysfunction, believing that a slow, broken process could achieve a systemic balance that a swift, perfect cure could not. This philosophy of achieving health through a guided imperfection did not stop at the human body. It was being applied with equal ingenuity to the very soil that fed the population, in the quiet revolution of crop rotation. A fallow field was not a sign of failure, but a testament to deep agricultural wisdom. Medieval farmers watched their most productive plots grow tired after years of relentless cultivation, their yields dwindling no matter how much manure they added. The solution was a radical act of patience. They would take that exhausted field and deliberately do nothing with it for an entire growing season. To a neighboring lord or a hungry community, this looked like madness, an admission that the land was broken. Yet this was a calculated surrender, a strategic pause that made the soil stronger than it had ever been before. Left to itself, the field was not idle. Weeds grew not as competitors but as green manure. When plowed under, they decomposed and returned vital nitrogen to the earth. Earthworms and burrowing creatures, no longer disturbed by the plow, aerated the compacted soil, creating a soft, sponge-like structure that could hold water and allow young roots to spread with ease. Most importantly, the life cycles of pests and blights that had specialized in attacking wheat or barley were brutally interrupted. With no host crop to consume, their populations crashed, granting the next year's planting a clean slate. Treatises like Walter of Henley's Husbandry did not see this as a loss. They calculated it as a long-term investment, proving through careful records that the bounty of 2 or 3 subsequent harvests from a rested field far outweighed the single harvest sacrificed. The fallow field embodies the final, most profound layer of this paradox. It demonstrates that true resilience is not about constant, relentless output. It is about rhythm, about a system's built-in capacity for rest and recovery. The field's peak function was not achieved by forcing it to produce, but by allowing it a period of acknowledged non-function. This cyclical understanding of strength through rest resonated far beyond the farm. It mirrored the guildsman's day of Sabbath, the warrior's winter in garrison, and the scribe's moment of quiet contemplation between pages. It suggests that the ultimate form of paradoxical engineering is not a crack in a beam or a dent in armor, but time itself, strategically withheld. How did the people of this era finally make sense of a world that so often operated on these baffling, contradictory rules? The very stones of their cathedrals whispered this truth, a philosophy not of what is, but of what is not. In the quiet cells of monasteries, theologians and mystics were developing a radical way of knowing called the Via Negativa, the negative path. This was not a system built on defining God with human words and concepts, but on systematically stripping them all away. Thinkers like Pseudo-Dionysius and Meister Eckhart argued that the divine was so far beyond human comprehension that any positive statement about God was ultimately a limitation, a false idol built by the mind. True understanding, they taught, could only begin in a state of acknowledged ignorance, in a sacred darkness that emptied the soul of its preconceptions. They sought God not in the light of certainty, but in the brokenness of their own understanding. This was not a philosophy of despair, but one of profound hope. Emptiness became a vessel ready to be filled, and brokenness a crack through which a truer light could shine. When a master mason looked at a cracked trebuchet arm, or a farmer felt the flex of his broken plow, this theological framework gave their observations a deeper meaning. It suggested that a machine's perfect, pristine state might be an illusion, a simplistic human conception that masked a more complex, divine reality. The machine's true purpose, its highest function, might only be revealed when it was fractured. The Via Negativa gave them permission to see failure not as a mistake to be condemned, but as a mystery to be explored, a potential gateway to a higher order of functionality. Why would a perfect gate shatter under a ram's blow while a bent one held strong? The answer might be that the bent gate was not weaker, but was operating according to a more profound set of physical and almost spiritual laws, laws that valued resilience over rigidity and dynamic response over static perfection. This intellectual backdrop transformed the workshop into a place of theological inquiry. An artisan experimenting with a fractured furnace lining or a cracked lute was not merely solving a practical problem. He was engaging in a form of applied mysticism, using the material world to explore the same paradoxical truths the monks contemplated in their prayers. The broken object became a mirror of the soul, which, according to the mystics, must itself be broken open, its pride and self-assurance shattered, to make room for grace. This is why the great cathedrals intentionally included a flawed stone, and why the most accurate clock required a chipped escapement. It was a humble acknowledgement that human perfection is an arrogant fantasy, and that true power, whether spiritual or mechanical, flows not from flawless strength, but from a sacred weakness willingly embraced. The legacy they left behind is not just one of clever machines, but of a whole way of seeing the world, where the path to ultimate strength begins with a courageous and deliberate act of breaking. The alchemist's crucible held a secret that every blacksmith and mason already understood in their hands. In the search for the philosopher's stone, these early chemists did not begin with pure, noble metals. Their entire art was founded upon the prima materia, the first matter, a substance they described as base, chaotic, and utterly corrupt. It had to be broken down through a calculated nightmare of processes with names like putrefaction and mortification. They would dissolve metals in powerful acids, let mixtures rot in sealed jars for weeks, or shatter crystalline structures through repeated heating and cooling. This was not a path to purification through cleanliness, but through a guided descent into filth and decay. They believed that within this state of total material brokenness, the hidden spirit of the matter was finally released, becoming receptive to a radical rebirth. A lump of lead was not valuable despite its imperfections, but because of them. Its very baseness was the necessary raw material for the great work. The goal was not to repair the broken substance, but to leverage its broken state as a launching point for a leap into something entirely new and transcendent. This mystical framework directly influenced the more practical workshops of the era. A metalworker attempting to create a new alloy would sometimes follow an alchemical-inspired process, first deliberately oxidizing a batch of copper until it was covered in a green, crumbling crust, believing this degradation was necessary to unlock a deeper, more stable bond when it was later mixed with tin to form bronze. The alchemist, in his quest for gold, was simply applying the most extreme version of the medieval paradox. He sought to make matter perfect by first convincing it to fail completely. This tradition provides a profound symbolic capstone to our journey through the age of paradoxical engineering. From the cracked trebuchet arm to the bent astrolabe, from the fallow field to the guild's leaked secret, we see a consistent pattern. The medieval world, in its mechanics, its economy, and its very philosophy, operated on a radical principle. True strength was not about building walls against failure, but about designing systems that knew how to yield, how to break in the right way, and how to integrate that brokenness into their core function. Their legacy challenges our own relentless pursuit of flawless efficiency. What hidden capacities for resilience and adaptation have we engineered out of our own world in our quest to eliminate every single crack? That master's split in the windmill sail was a signature of true craftsmanship. In the flat, wind-swept landscapes of Flanders and England, the most reliable post mills were not the ones with pristine, billowing canvas. They were the ones whose sails bore a long, vertical tier, carefully stitched at its edges to prevent further ripping but deliberately left open. A miller watching a storm approach did not furl these split sails in panic. He watched them with a calm confidence, for he knew his mill was now operating at its safest and most efficient. The secret lay in the controlled chaos of the flutter. In a strong gale, a perfect, intact sail would catch the wind like a solid wall, spinning the heavy millstones at a terrifying and ever-increasing speed. This was not a sign of power, but a recipe for disaster. The friction between the runaway stones would generate intense heat, enough to ignite the fine, airborne flour dust inside the mill, triggering a devastating explosion that could level the entire structure in an instant. The split sail was a built-in governor. As the wind pressed against the canvas, a portion of it would escape through the long, open seam, creating a turbulent flutter that bled away excess energy. This self-regulating tier acted as a release valve, capping the top speed of the sails and ensuring the stones inside turned at a safe, productive rhythm, no matter how hard the wind howled. But this designed brokenness did more than just prevent catastrophe. It also made the mill brilliantly adaptive. On a day of fitful, gusty winds, a perfect sail would lurch and stall, its power delivery as inconsistent as the breeze itself. The millstones would grind unevenly, producing a poor quality flour. The split sail, however, harnessed the wind's inconsistency. The irregular airflow around the tier actually created more torque in those sudden, powerful gusts, giving the heavy stones the extra push they needed to maintain a more consistent rotation. The mill with the torn sail could grind grain steadily through conditions that would leave a perfect mill languishing. This was not a hidden trick. Millwrights developed a precise vocabulary for it, speaking of the good tier and the master's split as essential features. Their maintenance logs show a clear pattern. They would meticulously repair a cracked gear or a worn bearing, but they would leave these functional flaws in the sails completely untouched, sometimes for decades. They recognized that this brokenness was not damage to be fixed, but intelligence to be preserved. The windmill with the split sail stands as a perfect synthesis of every paradox we have explored. It is the cracked trebuchet arm managing stress, the bent gate distributing force, and the adaptive rhythm of the missing water wheel bucket, all woven into canvas and wood. It achieved a higher form of reliability not by resisting failure, but by designing its response to it. This machine, singing its thrumming, fluttering song in the North Sea wind, challenges us to reconsider what we mean when we call something broken. Our own era worships at the altar of flawless performance, demanding systems that never break and interfaces that never falter. Yet the medieval examples we have journeyed through pose a profound challenge to this modern obsession. They suggest that our relentless pursuit of perfect, fault-free operation may be building a world that is brittle, not strong. True resilience, as the cracked trebuchet and the bent gate teach us, is not about preventing failure at all costs. It is about designing a very specific kind of failure, one that is non-catastrophic, localized, and even productive. This is the principle of graceful degradation, where a system is built to lose function gradually and predictably, giving us time to respond and adapt rather than shattering without warning. Contemporary science is now catching up to this ancient wisdom. The field of fracture mechanics deliberately studies how to control the spread of cracks in materials like concrete and ceramics. Engineers now design concrete with synthetic microfibers that create a dense network of tiny, controlled cracks as the material sets. This micro-cracking does not weaken the concrete. It actually makes it far stronger and more flexible, allowing it to withstand immense pressures that would shatter a perfectly homogeneous block. In complex systems theory, researchers have found that introducing a small amount of noise or randomness into a network can paradoxically improve its ability to detect faint signals, much like the broken water wheel's irregular pulse created a more stable grind. Even in computer chip design, engineers are exploring circuits that can tolerate a certain number of errors, trading a sliver of perfect accuracy for a massive gain in energy efficiency and heat resistance. The medieval approach reframes an object's entire life cycle. We see a cracked smartphone screen and declare the device broken, its life over. The medieval craftsman would have asked a different question. He would see that crack not as an end state, but as a new phase in the object's functional existence. Could that fracture be stabilized, perhaps filled with a resin that scatters light in beautiful patterns, transforming the flaw into a feature? Could the device's software be adapted to work around a damaged sensor, gracefully shedding functions while preserving its core purpose? This philosophy invites us to design things that are made to be broken in, not just used until they break. It asks us to see wear and tear not as an enemy, but as a process that can reveal a deeper, more seasoned character, whether in a pair of boots, a social network, or a city's infrastructure. By embracing this paradox that a system might reach its peak only when partially broken, we open the door to a more adaptable and human-centric world. Our technologies could become less intimidating and more forgiving, learning from their own imperfections to better serve our messy, unpredictable lives. Our organizations could learn from the guild that leaked its secrets, building in strategic vulnerabilities that force innovation and prevent arrogant isolation. Our societies could learn from the fallow field, understanding that constant, relentless output is not sustainable, and that resilience requires cycles of rest and recovery. The machines of the Middle Ages do not just show us clever fixes, they whisper a timeless secret about the nature of strength itself. Sometimes the crack is not what destroys the vessel. It is what allows the vessel to hold water, a necessary opening that makes the whole structure capable of containing something greater than itself. Our journey through the workshops and fields of the medieval world leaves us with a startling truth that a crack is not always an ending, but can be the very beginning of a thing's true purpose. The master craftsmen who deliberately fractured a trebuchet arm, the farmers who broke in their plows, and the masons who laid a single flawed stone in a cathedral wall were not celebrating failure. They were practicing a sophisticated form of collaboration with the unpredictable nature of reality. They understood that a system designed to be perfectly rigid would shatter under the first unexpected stress, while one designed with a calculated weakness could bend, adapt, and ultimately endure. This paradoxical engineering reveals that resilience is not the absence of breakage, but the intelligent management of it. Our modern world, for all its precision and power, often struggles with this concept. We build technologies and systems that demand flawless operation, viewing any deviation as a fatal error. Yet this very pursuit of perfection can make our creations brittle, unable to cope with the chaotic, messy demands of real life. The medieval approach offers a different path, one where we design for graceful degradation, where objects and institutions are allowed to have character, history, and even scars that enhance their function. The challenge they leave us with is to look again at the fractures in our own world, not as problems to be solved, but as potential to be unlocked. Where might a little controlled breakage make our technology more humane, our cities more adaptable, or our communities more robust? The answer lies in learning to see weakness not as a flaw, but as a hidden source of strength. We have reached the end of our story, but the conversation is just beginning. I would love to hear your thoughts on where you see this paradox at work today. Share your own examples of strength through weakness in the comments below.